So Imagination is, according to this slide, a global technology leader. So we've been around in the industry for a very long time, about 30 years now, 25, 30 years, something like that. Our main selling point is we design the hardware and graphics IP. So we design drivers and we design hardware for mostly mobile and automotive graphics IP. So we operate under the PowerVR brand. If you don't know Imagination, you might be more familiar with PowerVR. We have been here a long time, like I said. These includes our graphics chips on the left in the blue there, and we also do several neural network acceleration chips for AI calculations, neural network training and inference. And those are becoming more and more popular this day and age. We originally started in desktop graphics many, many years ago. We then moved to laptops for a while and ended up doing mobile and automotive, primarily mobile. That's what we're going to talk about today. Within Imagination, I am part of the PowerVR developer technology team. So what that means is we're basically a community-facing team. We speak to developers, and we offer a bunch of free, entirely free services and tools. This includes training and workshop sessions. So these come in public meetups where we'll have a group of developers and we'll have a chat, and we'll have a chat about the tools, about graphics, generally keep relations up. They also come in the form of talks, like the one you're currently attending, where I will train people on the tools and what we give and what we offer. We also do private training sessions for any developers that are interested. So if you'd like to look at the tools and you want us to give you a full explanation of how it works, and if you want to show us to show you more personally, we're more than happy to do that. Give us a ring, give us an email. I'll do it personally a lot of the time. The main thing we offer is at the bottom right here, and that's what we're going to mostly talk about today, is the PowerVR tools. These are a set of free software tools. They're all available online for free. You just download them and get going. I think there's like 8 or 9 of them. When you download those, those also come with the PowerVR SDK, which is a cross-platform programming framework on one side, but most importantly, it's a host of example applications. So if you want to look at how we implement physically based rendering or image-based lighting or deferred shading, whatever, there's a whole bunch of them there. Go online, have a download, it's all free, you can read through it, it's all open source. And if you give an email, we're happy to talk about it. The actual devs that work on these just chat to you guys, and no problem. So I mentioned I'm going to give you a quick introduction to the hardware architecture of PowerVR. We call this, and it's very well known in the industry, as tile-based deferred rendering. This is kind of significant for a few reasons. Because we're on mobile, we do have a lot more higher bandwidth restrictions. So tile-based architectures are useful for that because all the information that is used by the GPU can be kept on chip during fragment processing, saving costly memory transfers to the CPU and back to the GPU. It also ensures the lowest amount of processing cycles. That comes from the deferred shading part. Basically, I'm going to describe in the next slide, we have a section called hidden surface removal, which works by completely binning opaque pixels if they are occluded behind another opaque pixel. So this is kind of what the architecture looks like. I'll try to keep this kind of simple and brief so we don't spend a long time looking at this. But basically, geometry data is where we start. That's where the API sends information to the GPU. We go through vertex processing, clipping, projection, and culling. So those are all kind of standard graphics phases. We then go to tiling. This basically creates something called a primitive list down here. What that basically is a list of tiles, each of which contains a list of pointers towards geometry that's within that specific tile. We then go into the renderer. The renderer is going to be tile specific. So only one tile is going to go through this at a time, although it's obviously parallelized for multiple, but generally one per block. It'll be rasterize, and then we'll hit HSR and depth test. So HSR is what I mentioned a minute ago. Hidden surface removal. So, like I said, if a pixel is occluded by a completely opaque pixel, then it's binned, no fragment processing done, saves a bunch of cycles, basically. That's the idea. If there's an alpha test, it does call it a feedback loop. So we'll go back here. If a pixel is fully alpha tested, then we'll go back again, complete alpha blending, drawn to the on-chip color buffer where it can be used again for other processes, and then finally out for the frame buffer. So basically, what I want to remember from that is that the tiler and the renderer are the important parts. The tiler is usually used to refer to vertex processing, the renderer to fragment processing as a very basic outline. These are useful because we're going to be talking about a tool called PBRTune. And this is kind of the #1 tool that we use at PowerVR within my job when we optimize applications. When we speak to a developer and they say, hey, we need this improved performance, we'll go into this and we'll start looking at it. So it's a profiling tool. It uses real-time visualization of performance metrics emitted by the PowerVR GPU. The important part of that is the library that emits the GPU data is usable as a standalone. So if you want to skip the whole PBRTune graphics API client driver stuff, you can integrate it into your application however you want, using the statistics however you want. So I'm going to briefly run through the UI. This shouldn't take too long. But basically, this is the start. So it's very easy to set up. That's kind of the idea we want to go with all our tools now. It deploys to multiple target platforms, Android and Linux, using a server called PBRPerf server. PBRPerf server is nothing for you guys to really worry about. It's all backend stuff for us that basically just sends all the data from the device to PBRscope for it to catch it. If you are on a rooted device, you just insert the IP and connect, or click the Android USB device button if you've plugged it into your host device. If you're not on an unrooted device, the same is still applicable. The only difference is you have to download a PBR Hub companion app onto the device, and then the same process is just the same. So this is kind of the UI of PBRTune and what you're going to be looking at whenever you spend any time in it. This is what I spend most of my days looking at. I'm going to split it into 4 sections, give you a quick run through of what they all are, then give you a bit of a demonstration of how we use those 4 sections in an actual application. And then we'll go on further on later to describe some more advanced features, and I'll give you a full live demonstration of how we profile an application from start to end. So this is the compute counter table. This is kind of where those metrics I mentioned earlier are output. So there's a whole list of them. I think there's like 70 or 80 in total. And they're going to come from the GPU and just be listed here for you guys to see all the data. The bottom left is where we're looking at the monitor. This is kind of like a quick pit stop for information. So it's going to be the first place you look all the time when you're profiling an application, where you see your CPU loads, where you see your general counters, how busy your hardware is, and really just a quick pit stop. The center section is the timing graph, so this is kind of the actual time frame which you're actually profiling within, the blocks and the steps that your hardware is taking, and also what each block is doing during any given time frame. Finally, there's a property section on the side. This is kind of an information section, so you're going to just see, you click on some kind of information section within the GUI, and you're going to get a bunch of information on the side, including why it happened, what it's doing. I'll go into a bit more detail. So, like I said, the monitor, these are your CPU cores. So when we open PBRTune, when we start profiling, the first thing we do is we look at the monitor window, and we say, okay, what's going on in the application? How busy are the CPU cores? We get some basic information. How busy are the standard GPU counters? So how busy is the renderer block? How busy is the tiler block? How much memory interface are we getting? So if there's a lot of memory being transferred back to CPU because it's overflowing from the on-chip buffers, we can see it in there. Same for shader load. How busy is the shaders per section of the shader load? So vertex processing, pixel processing, compute processing, whatever it might be. We also, I think I've just clicked the wrong button. I have, OK. There's also a statistics report at the bottom, which is going to give you a bunch of detail about the frame. I'm not going to go into too much detail on that in this session, but I can teach you about it afterwards if you're interested. So Monitor is a bit special because we also have a standalone app. Again, this is kind of a way of you skipping the whole PBRTune GUI, going for a more detailed approach, a less detailed approach, and something really quick and fast. So this is kind of just an APK you can install on an Android device. It looks like this bit at the side, and you select values, counters that you're interested in. If you're interested in the FPS, in the CPU, in the pixel, whatever you want, and then you also display how you want it to be displayed. So if you want it in a graph form, if you want it in text form, and it'll just be overlaid on top of your application while it's running. It's really quick, really easy. That's kind of the whole point behind it, similar to the monitor in PBRTune. So this is your kind of huge list of counters. It does look quite intimidating, and it covers a lot of things. So it covers your tiler tasks, your render tasks, your shader tasks. All of those things have efficiency counters coming from the GPU. They're going to describe it in a bit more detail and show you sort of individual parts that are going through the graphics pipeline. So they're split into categories. This makes it easier for if you know that you've got a tiler problem or you know that you've got a render problem with the application. You go and look at the category that's appropriate to that and look at the counters underneath it, and you can get a very quick information on what the problem is. The information is displayed across different time periods, so you can look at over the last second, over a specific frame, over a specific view, however you want it to be displayed. This is all configurable, so that's the idea behind PBRTune, is you can configure it however you want. The timing graph is in the middle, and like I said, it's kind of the main focus of your application analysis. So this is where you're going to spend a whole bunch of time looking. It's split up into multiple timelines for each hardware block. So if you're looking at render-specific tasks, if you're looking at tiler-specific tasks, those will come up in different rows, and they'll be listed appropriately. So like at the top for this one, this is the compute tasks that are running as the application is profiled. Then it's the tiler tasks, and it's render tasks. It's the same for all of them. So the counters I mentioned previously, you can enable them and overlay them as a curve. So this is really useful for finding out which specific tasks cause a jump or a drop in a specific counter. So the hardware might change and say, okay, the render has suddenly become really active during these tasks, and then it drops off when we're doing more tiler processing. That's a really basic example. The same is true for like how active your shaders are, your cycles per pixel, how active they are as the time passes. These little rectangles you see are what we call timing blocks. So that's basically a GPU task being overlaid onto the timeline in a specific place. So an example of a GPU task might be if you did a bunch of API draw calls and a bunch of other API calls, whatever you might be doing, and then you did a bind frame buffer in GLES. Then all that information that you just stored in the draw calls is kicked to the GPU as a task, and that'll appear in the render block as one of these rectangles. They're split into three. Just to quickly show you, the top color is the process ID, so that you can avoid like system UI processes or surface flinger processes, whatever you want. The middle bit is the frame, so you know which frame you're currently working in. You can also just select current frame or select the frame you're currently looking at. So it only renders that information, but still a great overview for the rest of it. The bottom color is the render target. So you know which surface is being rendered to, which frame buffer is being rendered to. So you know if two tasks are actually associated, if they're drawing to the same thing, then they might have dependencies, that sort of thing. The final section is the properties window on the side. This comes in kind of two parts. So you can either have the properties for a specific task or the properties for a specific counter. The task comes in this information, so you get very general information about it, how long it took, what the current frame number is, what task this is within the frame, and what block it's associated with. You'll also get the reason for the kick. So this is the same as the reason I gave you earlier, where there's been a bunch of draw calls, and then a bind frame buffer has been done, and we can see straight away that's why this was kicked. We know what's happening here. You've also got information for depth and stencil buffers going on, the surfaces being rendered to, and the surfaces being used in the render at the moment. If you scroll further down, you get shader information. So this is for the whole task, and you'll get information on how many shaders were executed, how many cycles each shader took, how utilized the shader cores were during these shaders. And you'll also get access to the GLSL source, which has come up in the wrong place, but if it's actually that hyperlink right there, if you click that hyperlink, it'll come up as a source view. This is kind of a miniaturized version of a tool we have for shader profiling and analysis, which shows per line shader cycle counts. So you can debug exactly which lines are most expensive. If you pour this into the actual tool, you'll also get a full shader disassembly, where you'll get all the shader machine instructions that come from the shader. So you can see what happens when you remove a specific shader line. It'll turn into machine instructions that you can remove, add, try modifying it, whatever you want. But yeah, within this, you just get a quick view of it, which shows you what the most expensive lines are. If you enable if you click a counter, you'll get a counter properties window. This is kind of for people who are unfamiliar with our hardware, or if you just don't know what a counter does and you're kind of unsure of what it means. You get some description, you get general information of what it does. You also get, most importantly, what a high value means or what a low value means. So you'll know, like, okay, this is a really high value, and I'm not sure if that's a good thing or a bad thing. You get information here that says, okay, it's bad because this, and you can also try looking at this to change it. So in this case, it's like it's been active for the render task has been active for a significant amount of time. There could be a lot of texture fetches and memory latency incurred from this. You also get access to the actual equation that we use to calculate it. So if you're still not sure what it is, you still want to go lower level, you can find out exactly how we calculate these counters right there. So there's a number of advanced perf server options which I want to talk to you about. But first, I'm going to quickly just show you all of that in action on a really simple demo. So this is the original recording window I mentioned earlier. You can just click on a USB device to connect to it or connect to an IP. I'm going to open a pre-made task, a pre-saved file that I previously had. That's something you can do within PBRTune, is you can save a file and relook at it. I'm going to disable quickly some of the unused timelines so we get a simpler look here. But basically, that was a full application recording. I think it's about 20, 30 seconds long. As you can see, it loads very fast. And we get straight into it. So on the left, we have our counter window, our counter tables. Like I said before, you can overlay whatever you want. So if you want to know how active the render is across the whole application, you can see it listed here as hovering at about 90%. If you want to see how long a frame time took, you can overlay that, and it'll say, okay, it took 12 milliseconds for this frame to be fully rendered, whatever it might be. The monitor is here for the quick stop, so if I was doing an analysis, this is where I'd be looking straight away. I can change the time period which this works across, so I can change it to a line, and then the values will update as I move the mouse if I want to look at a specific part that's got bad performance. And if I want to know more about a counter or a task, I've got this section over here, so I'm currently looking at the render active task. If I want to zoom into a task, click on it specifically, I get a bunch of information showing this is the process ID, is our demo application. It kicked because the flush buffers task occurred at the end of a frame. During this task, there were 37 draw calls, blah, 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 blah. Pretty much everything you could possibly want to know about the current task. So there are a couple of more advanced PBR perf server options. These are kind of what we use for really advanced application analysis. If we don't want to just know, okay, is it render blocked, is it tiler blocked, we'll look at these. So you can override the perf server options just right here in the recording window. And those come in. The two things I'm going to talk about, there are a couple more that we're releasing soon, but these are the two I'm going to be mentioning today. Firstly, the client streams. So this is kind of, for those of you who are familiar with tracing tools, this is kind of a trace overlay of the API calls that are being made in tandem with the GPU tasks that are being incurred by them. And then the synchronization objects, which is, I'm sure any of those of you that are familiar with Vulcan will be aware of. In Vulcan, those are fences and semaphores. In GLES, it's all handled by the driver, but they're still present. So client driver streams, these are going to be enabled under the host user mode section. In this case, these are the EGL and the GLES for our test app. You can also use Vulcan and OpenCL. So we most commonly use these for Vulcan and GLES applications, of course. And basically, they're just going to render the per API block. So one block that I mentioned earlier becomes like a single API call, so draw elements or bind frame buffer. And then you can see straight away when it calls bind frame buffer, that kicks the tiler tasks, that kicks the renderer tasks. It makes it all very visual and very lined up. Synchronization objects, as it says here, are used by the driver to ensure that operations queued by the driver are executed to the GPU in the correct order. So that's what a synchronization object is, in case you're not aware. Basically, it's for making sure that a resource is ready before another operation uses it. You can enable these per hardware block. So if you want to enable specifically render synchronization objects, you enable the render queue, hardware queue. That will show a bunch of them stacked on top of each other, located underneath the render tasks, and you'll see like when the one becomes available, it then kicks the render task, and so on and so forth. It's also, if you're aware of the specific synchronization objects you want to look at, you can just enable that on its own. These are actually GLES ones from our driver, which you're welcome to look at. But you also get the Vulcan ones if you're using Vulcan. This is kind of what it looks like. So the red bit at the start is when it's checking for a buffer resource to be ready. And if it's hitting those red lines, that's where it's failing. It's saying, OK, the buffer is not ready yet, or the resource is not ready yet. So keep waiting. When it turns green, it's passed, the resource is ready, and this kind of muddy brown color is when, OK, everything's fine, the task is running. And gray is when it dies. So the main part of this presentation I wanted to give was a complete demonstration of how we do this in the office and what we use this tool for in terms of actually profiling applications we look at. So I'm going to come back to here, and I'm going to open another demonstration. This is just a full recording of the Manhattan benchmark. It takes, I think the actual demo we recorded was about 50 seconds, a minute long. It includes shader compilation, full API setup, everything, and that was all just opened in the case of, I don't know, it took maybe like 5 seconds to open there. So it's not a slow tool, everything is as streamlined as we can possibly do it, and we're good to go. So same as before, the first thing I usually do is remove all the information I don't want to look at, of which there is quite a bit. So this is the one I'm keeping here is the client stream for Manhattan, or the demo we're looking at. I'm going to remove 2D information because I'm not really interested in that, and I'm going to keep the compute blocks data, the compute sync object data, the render object data, the render sync object data, and the same for Tyler, and then this one at the bottom is the GLES task I was talking about. So first things first, I'm going to hypothetically say we were told to look at this application and say, okay, it's got a bit of a performance problem. This is low-end hardware. We want to improve it. We know that the FPS is hovering at about 20 or something, and it's dipping at some point. We want to know why. So first I'm going to look at the whole application, just say, okay, the CPU is not that active. We're setting about half, sometimes down to a quarter. The memory interface is not bad. There's not a memory interface problem. We're not going to be dumping a bunch of memory down to the CPU. The shaders are quite active. We're sitting about half, so they are quite busy. But that's fine, because we know this is a very heavy graphics application. And then the same is true for render active. That's quite busy, but we know it's a very busy render application. And a render active being very active is not always a bad thing. It's quite often a good thing if the hardware is fully utilized. So we know that I've been told that the frames per second is holding steady and then sometimes dipping. So if we open it up and we look at the FPS over time graph, this is for the full view of the application. So it holds up about 20 frames per second, all the way along here, and then at one point it dips down to about 14 frames per second. So we know this is the bit they were talking about. This is what I was told to look at, and I just need to find exactly why this dip happened. So there's a few reasons for this, but the first thing I'm going to do is try and find out whether it's a CPU problem, whether it's a GPU problem, try and narrow the task down a bit. So I'm going to use the monitor I mentioned earlier to do very general information. I've changed the time period to line, so I know that the data is updating as my mouse does. Make that a bit bigger so we can include it. So we can see everything is changing as I move my mouse. I'm going to compare the data when the frames per second is good to the data when the frames per second is bad. I can see that the CPU here is fine. These are all the stuff I was looking at earlier. And I'm basically just going to look at this and see the difference as I move my mouse over here. Most things are becoming less active by the look of it. The only things that we can see are definitely increasing are the shader load and the render active. So this points us straight away and says, OK, we know that it's probably a shader problem. And we know that it's definitely on the render side, so it's probably a shader problem, basically. So we know a few things about shader problems. First thing, there are 3 different types of shaders that we're using in this application. We're using compute, pixel, and vertex problem shaders. So if we go to the shader section under our counter table, and we'll try and narrow down which one of those it is. So if we look at compute shaders, sorry, I still want the FPS there. If we go down to compute shaders, and we look at the bottom, this counter at the bottom is the shader. I'm not sure if you can quite see it on the board. You just click on. It holds at about 2% active for pretty much the whole time. There's a very low load in the compute, and then it actually dips at the same time as our FPS dips. So not a compute problem. We'll do the same with the vertex, and we'll see the same thing. Holds about 1.6, and dips to about 0.7, so not a problem. The vertex load and the compute load are not having a problem. The next thing we'll test is the pixel processing load. So it hovers at about 40%, and we see the opposite here. So we're actually seeing it spike up to about 70% load on the pixel processing at the same time as our FPS is dipping. Not a confirmation of a problem, but definitely a strong indication that something has changed in the pixel processing here, and it's made it a lot more expensive to process all the pixels and to render this frame for a little while. So we know it's a pixel processing problem, or we're very sure it's a pixel processing problem. There's 2 different types of pixel processing problems, or any kind of shader processing problem. They can be either a texture problem or an issue in just the number of cycles and the amount of calculations that are being done inside a shader. So if we check if it's a texturing problem, we'll go to the texturing counters and we'll enable texturing active. And this basically shows how active texturing was during the processing of these frames. So it hovered at about 93%, and then it dipped to about 90% during the dip in our frames per second. Not a texturing problem. All that leaves for us now is an ALU problem or a cycles problem within the shaders. If we enable cycles per pixel, we can see that at the same time as the FPS drops, the cycles per pixel really spikes. It goes from about 30 cycles per pixel up to about 60 cycles per pixel at the same time as our FPS dips down to about 14. So this is definitely a problem. We now know that it's a fragment processing problem, and we know that it's an ALU fragment processing problem. So a shader is being very busy, something is being added. All we need to do to find out now is exactly what. So I'm going to zoom in right up close to the tasks that are being done during this time period. When you zoom in, obviously everything gets a bit larger, and you can see a bit better. All I'm going to do here is try and look for the task within a frame. So I've selected a specific frame here. I'm going to try and look for a task that's extremely busy and taking extremely long. So pretty obvious which one it is, but I'm going to go through anyway. So task 14 takes 7, task 13 takes 10, task 8 takes 4, takes 2. Task 3 is taking 50 milliseconds. So this is what's causing a huge holdup in the whole rendering process. We can see here it's taking 49.6 milliseconds, which is way longer than all the rest. So I know it's a shader problem, so I'm going to go into the properties window here, and I'm going to look at the shader information, what shaders are executed, and which ones are taking the longest time. And basically, all I'm looking to do here is narrow it down to a specific shader, so that for me, I would be telling the developer the shader is causing a problem, or if I was the developer, I'd be knowing which shaders I can change to make the biggest difference in my application. So 9 shaders are executed as part of this task, and they're all listed here. We're going to look through the cycles and find the biggest ones. So this one here is 13, this one here is 39, this one here is 39. We'll go through them until we find one that's really high, not really high, but fairly high. In this case, these are 5, 6, this one's 66. So we can fairly certain that this shader is causing a problem across all of these rendering tasks. If you wanted to confirm, you could look at another task that's also equally large and find the same problem. You've now got an index for the shader. You can see how busy it is, how many temporary registers it's using, and the instructions it's using. And then usually what we do is we just open the GLSL source, we click this button, and a source view would come up, or not. Anyway, the source view you saw earlier would come up. I'm not sure why it's not. You then get the source that your shader is actually processing. You'd know exactly per line where the problem is, and you'd be able to narrow it down to that shader, pass it to the application where you could test it. If you remove that shader, does it suddenly get much better performance? If it doesn't, then you're wrong, do it again. If it does, okay, you found your problem. So that would be for a specific case of profiling an application. If I was doing more general case application, I would look at how active a render is, how active the tiler is. And generally speaking, when you're creating a graphics application on mobile, you want the tiler and the render to both be 100% active in an ideal world, running in parallel, one on top of the other. In a realistic world, that doesn't really happen, but we are trying to get as close to that as we can. So if we look at how active a render is in our time for this application, we can see that it's about 90%. So there are problems here where we could see, okay, maybe we could make this more active. We could find out what the stalls are in between tasks that's causing this. So if we zoom in and look at the per tasks as we did before, we're basically looking for a break. So you can see that the biggest break here is about 5 milliseconds during the space in between rendering tasks 3 and 4. And we're basically going to try and find a general reason for why this might be, see if it's something we could change, something we couldn't. In most cases, you can't change this. Sometimes it's an application or a driver error. We're going to try and find out which. If it's an application error, you can change it, you can update that. If it's a driver error, we can pass it on and we can find ways to update that as well. So in this case, we're looking at a transfer task here. So a MIP generation task is what's waiting on something for it to catch up. So we're going to look at the synchronization object tasks, synchronization objects associated with these tasks, which in this case is this one right here. As you can tell by it becomes ready at the same time as this task is running, and then it's running for the same duration as this task. So we've got the appropriate synchronization objects, and we're looking for what else is waiting for this point. So the compute queue tasks are waiting at the same point. It looks like it's all becoming available at the end of this queue task. If we want to confirm that that's the case, we look at these compute tasks and look at the render target. So the render target is this yellow color. If you want to actually look at them individually, you can look at the data addresses and stuff and see if they match. But basically, we know that these are associated with the same render target. We know that this is waiting on this render target to become available because it's doing something with it in the compute tasks. Since it's a MIP generation task, there is probably a OpenGLES task on it, waiting on it, which there is here. It's an extremely long one, which is quite unusual. We know that the API now is waiting for something before it can do its next task, which is probably some kind of texture allocation or rendering using that same texture. In this case, it is a texture allocation that's going next. Ideally, we'd want to see if the application could do the other render tasks first. So if we could do render tasks that aren't waiting for that resource before it does the rest of them, then obviously that's far more efficient, and they can run in parallel to the compute tasks. This will be down to the application to actually find out, but what we can do here is look at these tasks, and we've said straight away, okay, we know that there's a map generation task. We know it's associated with this third render task in between the third and the fourth render task, and we know that it's caused by this compute. So we look in the application and see, okay, is there a way for us to free up resources so that they can run at the same time? If there's not, maybe speak to us and say, okay, do you have any idea why this is happening? Why is this such a long MIP generation task? And what can you do about it? So the basic lesson to be learned here is if you see something very strange within PBRTune, speak to staff, which is me, and say, okay, what do you think? And we might be able to say, okay, your application is probably doing this. Can you change it? Alternatively, if neither of us can figure it out, we'll say, okay, we'll speak to the drivers team and see what we can do, and then we'll push a driver update to fix whatever the problem is. So it benefits both of us. I think that's kind of everything I wanted to show you within PBRTune. I hope you understood everything I was talking about. And I hope you had a really good reboot. I've been told, as I'm sure you've heard this a trillion times today, but we are actually hiring, surprisingly enough. I hope you're not bored of hearing that. And I've been told to also pass on that you can find it on the website, or you can speak to me, however you want to, if you're interested. If you're interested in our tools and SDK, those are also available on the website. And other than that, thank you for attending. Hope you have safe travels home.
Do we have any questions, maybe?